Hello everyone, I'm Paul and today we're solving problem 231, power of 2. This is an easy one, so this will be quick. Our job is simple. We are given an integer n and we need to return true if it's a power of 2, otherwise we return false. And here we have like a small hint. We know that n is greater or equal to minus 2 to the power of 31 and smaller or equal to 2 to the power of 31 minus 1. So basically we can have 32 bits in n. And the first observation here is that we don't care about negative numbers. Why? Well, because we will never find a power of 2 that's negative. So in this case we just return false. So we can forget about this part and we say that n is smaller or equal to 2 to the power of 31 minus 1. Now let's say n is 16 and this is the base 10 representation of this number. And if we transform this to binary, this is 1, 0, 0, 0, 0. So this is the base 2 representation of 16. Now just by looking at this, I already know that this is a power of 2, so we return true. And how do I know this? Let's take this number. We know that if we want to transform this number into the base 10 representation, we need to do the following. We go from right to left from position 0, meaning from here, and each time we do 2 to the power of the current position times the current bit. So this is position 0, and here we have position 1, 2, 3, 4. So we do 2 to the power of 0 times 0, this is 0. This times 0 is 0, this times 0 is 0, this times 0 is 0, and 2 to the power of 4 times 1 is exactly 16, which is our target. So we see a pattern here in this binary number. If n has a 1 and then every bit after 1 is 0, this means the number is a power of 2, so we can return true in this case. So there are many ways to solve this, and here I will show you 2. We can iterate every position in this number with a new value. We can call this current, and this is initially 2 to the power of 0, meaning 1. So we are here initially, and every time we are doing current times 2 to move to the next position. So first we are here and we are checking if current is equal to n. In this case it's not, and it's smaller than n, so we can continue and we move to the next position, meaning we do current times 2. This is 2. So now we are here and 2 is not n and it's smaller than n, so we can continue to the next position, and 2 times 2 is 4. So now we are here and 4 is not 16 and it's smaller than 16, so we can continue, and 4 times 2 is 8. So now we are here and 8 is not n, so we continue. 8 times 2 is 16, meaning now we are here, and 16 equals to our target, so given that we found the target, we can return true. Now if we reach a point in which current is greater than n, here we just return false. Now this is just one approach. Now we will show you another way to solve this. Let's say n is 16 again, and this is the binary representation for 16. And now let's say we get the binary representation of 16 minus 1, meaning 15. So the binary representation for 15 is this. And remember what I told you first. I knew this was true as soon as I saw it because it has a 1 in the leftmost position and then every bit is 0. So we are checking the same here. We take 16 minus 1, meaning 15, because if this is a power of 2 and we do 15 bitwise and 16, the result should be 0. Remember that this operator returns 1 only if 2 bits in the same position are 1. In this case we have 1, 0, this is 0, and here we have the same, and here we have 0, 1. so we also have 0. So the result of 15 bitwise and 16 is 0. And this is exactly what we are looking for. This means we have one bit that's 1 in the leftmost position in 16, and then every other bit is 0. So given that the result is 0, we just return true. If the result was not 0, we will return false. As you can see, the key here is to visualize this in terms of binary numbers. So now let's go with the code, and hopefully you will get the idea. For the first approach, we say current is 1, meaning 2 to the power of 0. This is the bit at the rightmost position in a binary number. So now we can iterate the binary number. We say while current is smaller or equal to n, we update current. This is times equal 2. And before this, we are checking if current is our target. And if this is the case, we just return true. Now, if we end this loop, meaning current is greater than n, and we haven't found our target, this means we need to return false. So this is it for the code. Now let's submit this and see if it works. As you can see, this works and it's very efficient. Time complexity here is big O of log n, and space complexity is big O of 1. So now let's go with the code for the second approach. This is a very short code. First, we need to filter negative numbers. So we say if n is smaller or equal to 0, we just return false right away, because we'll never find a power of 2 that's a negative number. Now, if the number is positive, we just return not n bitwise and n minus 1. And remember the drawing we saw a few minutes ago. We are just checking if n has a bit that's 1 in the leftmost position, and then every bit next to that one is 0. And if that's the case, we return true, because this should return 0. That's why we use the word not here. So if this returns 0, we return true, and otherwise we return false. So this is it for the code. Let's submit this and see if it works. As you can see, this also works and it's very efficient. Time and space complexity here is big O of 1. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.